Okay, so now given our knowledge about standard forms, let's define one thing called basic solutions. These basic solutions turn out will be related to extreme points of the standard forms. Okay, so suppose we have a standard form linear program with m constraints and n variables. So this m constraints refers to inequality constraints. Okay, so that means this matrix A is of dimension m times n. Okay, m by n. Here we may assume that rank A is m. That means all the rows of A are independent. So here we're saying that this assumption is without loss of generality. So I would suggest you to think about this. Why may we assume all the rows of A are independent? Okay, turns out this is true, but I encourage you to think about that by yourself. And then, if we accept that this is true, this will imply that m cannot be greater than n. If m is greater than n, it's impossible for all the rows of A to be independent, right? So m is less than or equal to n, and because if m is n, then the problem is too trivial. There can be at most one solution. We just get, one feasible solution. So either that's optimal or the problem is infeasible. So in the below, we will assume that m is less than n so that this problem is hard enough. So for the system, now we can see that there are more columns than the rows. Okay, so let's select some columns to form one thing we call basis. A basis B is a standard form linear program. A basis B of a standard form linear program is a selection of m variables. Okay, so among all those variables, I select m of them, so that by collecting those corresponding columns, I can get a square matrix. I call it AB, so that it is invertible or non-singular. So we know that for A, this matrix is somewhat flat. Okay, the number of columns is larger than the number of rows. So what I'm doing here is that I collect some numbers, some columns. So in total there are m rows, right? So I collect m columns out of the total n columns. I collect m columns to get AB, and this AB should be invertible. Okay, so if this AB is not invertible, then these m columns do not create a basis. One thing to keep in mind is that these basic columns do not need to be close to each other. So for example, you may take some of them here, another column here, and some other columns. Okay, you collect these columns and put them into one single matrix. That's called AB. Okay, so what we're doing is actually ignoring all other n minus m variables, and that means this ax equals b will be changed to another linear system because some variables has been ignored or some columns has been ignored, and the result is that we need ax equals b to have a unique solution because ab is invertible. Okay, that's exactly what we are doing for a basis. With that, we now can define basic solutions. A basic solution to a standard form linear program, satisfies the following two things. First, n minus m variables are ignored, or that means are set to be 0. And then the remaining variables can satisfy ax equals b. So these n minus m variables, and they are chosen to be 0, and they are called non-basic variables. Then the other m variables are certainly called basic variables. Those columns are called basic columns, and the collection of those m columns is called a basis. Okay, so here one thing to remind you is that these m columns together must form a basis so that AB inverse is invertible, so that AX equals B has a solution. We're going to use XB and XN to denote the basic and non-basic variables given a basis. Okay, so keep in mind that we first have a basis and then we define basic and non-basic variables. Non-basic variables are those variables not selected in the basis. They are set to be 0. And then for the basic variables, their values are calculated according to AX equals B. And here, because A has been reduced to AB, or the submatrix, right? Because all other columns are somewhat multiplied by 0. So what we are really solving is ABXB equals B. Okay? Now we only have these M columns times M variables, and XB can be expressed as AB inverse B. One thing to keep in mind is that for basic variables, they may be positive, negative, or 0. We have no idea about what will be their values. Their values depend on the selection of B and cannot be predicted in advance. You may only have these values only if you solve the linear system. So, to give you some example, suppose I have an original linear program like this, and then I have the standard form problem by setting up the equality constraints with these two additional slave variables. For the original problem, the graphical feasible region is depicted here. Okay, here you may have already observed one thing. When we were defining basis and basic solutions, we don't really care about the objective function, right? We only care about constraints. So that's why here, when we want to draw some graphs regarding basic solutions, we can just ignore the isoprofit line or the improving direction, whatever. We only care about the feasible region. Anyway, I have a standard form now. For that standard form, I have two equality constraints and 4 variables. So that means according to my formula, each time I need to select 2 basic variables to form a 2 by 2 AB matrix. Okay? And then I have the remaining n minus m 2 non-basic variables. So now, what's the steps for obtaining a basic solution? I first determine a set of m basic variables to get a basis B, and all others will belong to the non-basic variable set n. Non-basic variables are then set to be 0, and then I solve the remaining m by m system ABXP equals B. Okay? So for this example, I will solve 2 by 2 linear systems for those given bases. So let's continue. I have these two equalities, okay? And if I try x1, x2 as my basis, the other 2 variables are in non-basic variables, then how may I get the solution? What I should do is to solve this 2 by 2 system, okay? Because I collect these 2 columns as my basic columns. So this is my AB XB, okay? Because my AB, this submatrix is 1, 2, 2, 1, okay? ABXB, and certainly this guy is the small b, okay? 6, 6. So I have this 2 by 2 linear system using Gaussian elimination or whatever method you have. You may find a solution as 2, 2. So basic variables are 2, 2. Non-basic variables are 0. So this basis gives me a basic solution 2, 2, 0, 0. Or I can choose another basis, right? Suppose I choose the second column and the third column. I get another linear system. This solution is 6, negative 6. So collectively non-basic, basic, basic, non-basic, I get 0, 6, negative 6, and 0 as this basic solution corresponding to this basis. So now immediately you have this idea. Because we choose m out of n variables to be basic, we have at most n choose m different bases. Okay, so try to think about why here I use at most instead of exactly. When do you see less than n choose m different bases? Okay, but in this example, we have exactly 6 bases. As I mentioned, this is by coincidence. It's not always exactly. Think about that. So, by examining all the 6 bases one by one, we may find all the associated basic variables. Okay? If I choose x1, x2 to be the bases, then they may have some values. x1, x3, then I solve another linear system. For those variables chosen to be non-basic, they must be 0. Okay? So this is a complete list of my basic solutions. One thing to remind you is that for a basis, what matters are variables, not values. I use the following example to do this illustration. Suppose I give you another example like this. Again, a 2 by 4 coefficient matrix A to represent this standard form problem. And the feasible region is here. As you can see, 2 constraints and one more non-negativity constraints, they intersect at one single point. Here, if you repeat the whole process by yourself, for example, choosing x1, x2 to be a basis to find a basic solution, and then x1, x3 to find another basic solution, and so on, you will see the following things. 3 different bases result in the same basic solution. Okay? These 3 bases, they are indeed different because this is x1, x2. This is x1, x3. You are choosing different columns to be bases, right? You're choosing the first and second, you choose the first and the third, they are different bases. But accidentally, they correspond to the same basic solutions. Okay? 3 different bases gives you one single basic solution. That's possible. And again, you cannot predict that in advance. Only after you solve for the values, you can see that happens. So, for this example, there are 6 distinct bases, but only 4 distinct basic solutions. Okay? So, we have the following inequalities. The number of distinct basic solutions is less than or equal to the number of distinct bases, which is less than or equal to n choose m. So, when multiple bases corresponds to one single basic solution, we say the LP is degenerate. Okay, for example, this is a degenerate case because multiple bases corresponds to one single basic solution. For the first example, it's non-degenerate because basis and the basic solutions has a one-to-one correspondence. So we will discuss degeneracy at the end of the next lecture, okay, because that's going to create some issue. At this moment, let's assume all the LP are non-degenerate. Okay, thank you.